So guys, myself Avichal from Softcell Technologies, and I'll be taking you through this session on basically 3D tolerance analysis using CETOL Six Sigma tolerance analysis tool. Okay, that is part of Sigmetrics portfolio. Sigmetrics is a US-based company. So let me just start off with a quick introduction about Softcell first, and then we can talk about what is CETOL, how it can help with 3D based tolerance analysis, and then we can look at some live demonstration for automotive engine assembly also. Okay, so Softcell has been working with within this engineering services domain from last 20 years. The company is 30 plus year old, and from last 20 years we are working within this engineering services domain, primarily working with PTC for the CAD, PLM, AR, IoT solutions from the PTC portfolio. That includes Creo for your product design. Then Windchill is for the product lifecycle management, which takes care of the complete life cycle of your product, going through different stages from design to quality manufacturing and all that, including requirements, documentation, and the service life cycle as well. Then comes Sigmetrics, so that is for 3D tolerance analysis. US-based company that is primarily working in the tolerance optimization domain. And then ANSYS, as you're probably aware, with respect to all kinds of simulations, whether it is structural, thermal, CFD, electromagnetics, light simulation, and then Moldex 3D is for the plastic mold flow simulation. Based out of the locations across India. Now coming to Sigmetrics. So Matrix is a US-based company. They are the global experts in GD&T and mechanical variation. And for over 25 years, they are working on building, this solution, adding more and more capability to it. CETOL Six Sigma is the main 3D tolerance analysis solution, which is compatible with all of your major CAD platforms, including CATIA, NX, Creo, and SolidWorks. So I'll be showing the live demonstration with PTC Creo, but in terms of the capability, it has same capability with other tools also. Okay, and apart from CETOL as an analysis tool, Sigmetrics is also helping customers with GD&T training as per your ASME or ISO standards through some computer-based training programs, and there are other trainings also with respect to MBD, model-based definition or model-based enterprise, because that basically complements tolerance analysis also. I'll talk about that later, how that helps with your say your CAD model-based tolerance analysis rather than doing it manually using Excel sheets or using manual calculations. So this is the portfolio from Sigmetrics, including CETOL for the complete 3D based analysis, which covers all 3D variables and considers all 3D variations and then gives you the result. Now that is again, as I said, compatible with these CAD platforms, Creo, SolidWorks, CATIA, and NX. EasyTOL is a one-dimensional tolerance analysis tool, which again works with the same CAD platforms, including Creo. It comes as a as an extension module within Creo that is limited to one-dimensional stackups. And then GD&T Advisor is again embedded in Creo, and it helps with the correct application of GD&T on the 3D data. So that is basically where it also helps with the MBD process. So if your company is, like most of the companies are still, using the traditional method where they are making a 3D part assembly, making 2D drawings for all the individual parts, and then putting all the dimensions, tolerances in the 2D drawings. Okay. Now, that process is not very effective. It's not very efficient because it doesn't really help the user with correct application of GD&T. People can make mistakes easily, and that increases that cycle time because you have to go through the drawings, rectify the mistakes, and there are multiple engineering changes happening because of that. So that takes a lot of time. So GD&T Advisor really helps in that aspect. It helps in reducing the time that is spent on drawing creation because you are applying GD&T on the 3D data itself. and that's faster and that's more accurate also. Okay, in terms of correct GD&T application using the right symbols basically. So this is a separate topic. I'll not be covering GD&T advisor or EasyTOL in this session. I'll be primarily working on CETOL, showing CETOL capabilities. We can probably plan another session for this GD&T advisor and EasyTOL in the coming webinars. Okay, so this is the customer landscape showing different industry verticals. Companies within different industries, how they are using CETOL, whether it is in India or US or Europe region. So I'll just name some of these customers which are also using CETOL in India. That includes John Deere, if I talk about automotive OEMs or heavy equipments, construction machinery or tractor divisions. So John Deere, Caterpillar, Case New Holland is one more customer, CNH, and Cummins, FCA, Fiat Chrysler. Then coming to the supplier domain, ZF Electronics, Hyderabad, Borg Warner, Continental, and then Veltor, Bangalore. And in the consumer domain, Whirlpool, Pune, they have been using CETOL from quite some time. Eton Electric in the power sector, where we are primarily working with electrical uh, industrial products, including circuit breakers, MCCBs. So Eton is working heavily on those. Also Schneider in the same domain in Bangalore. Then coming to medical industry, we have some uh, customers all across India, like Philips is in Pune, CETOL, Pune, Stryker in Gurgaon. Next is one more customer in Bangalore, utilizing CETOL for the tolerance optimization for medical devices. Okay, so since I'm focusing on the automotive segment in this session, I'll be talking more about automotive-based customer references, case studies, and the live example will also be with respect to engine assembly. So guys, if you have any questions, you can also mention it in the Q&A section. So I'll be just going through the questions and answering them. Okay, so these are the various segments within automotive, like powertrain. These are the customers in the powertrain segment using CETOL. Then chassis, interiors, body vehicle, these are the sub-segments. And these are the various customers in different segments using CETOL. Now, talking specifically for the automotive-based case studies, this one is from Caterpillar for their diesel engines. Okay. And the problem, in this particular case was that instead of belt drive, they wanted to use gear drive because of the loads and vibrations involved. They wanted to use gear drive, and while while changing from belt drive to gear drive, obviously the orientation of these gears becomes critical for the smooth running of the gears and reducing the wear and noise and all that. So that heavily depends on the orientation of these gears. Okay. Now with CETOL, they were able to identify what all features were critical in terms of the orientation of these gears. So that's where they were able to find out critical to quality dimensions, or you can say highest contributors towards the gear train quality. Okay. And then they went back and redefined the tolerances for those critical features and ensured that the assembly functionality and fit and function will be achieved without adding too much cost for manufacturing. This is for ZF for the door latch assembly mechanisms, and with the prior process where they were doing manual calculations or Excel based calculations, they were spending around 60 hours on each new assembly design. Okay, so they were spending a lot of time, and still they were making on average 3 prototype iterations at a cost of $8,000 per prototype iteration. So basically, they are spending a lot of time going back and forth between design and manufacturing, between design and prototyping. That led to high high design cycle time, and still they were not getting the correct results. So still they were facing problems with respect to the door latch assembly. Like it could potentially send a signal that it is locked when it was actually not locked. So there was a significant safety concern there. Right. Now with CETOL, they were able to first reduce the time that they were spending on each new stack up. The designs were free of surprises. So any potential problem that may be identified in the prototyping stage was identified in the design stage itself and rectified there itself. And then again, they were also able to relax tolerances in some areas because not all parts are equally critical, right, for the assembly variations. So they were able to identify which parts are more, let's say, critical to quality, CTQs, which require higher precision for correct assembly functionality. Okay. So if I talk about the benefits of CETOL, obviously, the business benefits are in terms of, the development cycle time reduction, the reduction in product development cost, right? And then preventing warranty issues, uh, reducing number of prototype cycles. So that is obviously from the business benefit side. But as a user, when you're working on the tool, these are the functional benefits that you would also find interesting. So the first one is obviously the 3D based assembly variations, where you can check the impact of each variable individually on your assembly variation. So for example, here we can see that this particular feature, let me add some annotations here. So here you can see that this particular feature, mid cam pivot hole. So this is a whole feature in the plate, side plate. Okay, so this is the part and this is the whole feature. So this has four variables, TX, TY, RX, RY, basically two translations which define the location of the hole, and two rotations RX and RY which define the orientation of the hole, the axis orientation. Okay, so all these four variables are taken as input towards the assembly variation. So we can identify how much of impact is there on the assembly variations with respect to each input variable like TX, TY, RX, RY. So we can get the individual contribution from each of them, and that's where we can get this contribution list. So what you see on the right side, this list of contributors, that is basically showing what is the impact of each variable on on assembly variation. So we can see that this 16% is there from the mid cam pivot hole itself. Basically, the same feature has 16% impact, right? And likewise, it will see all the rest of the variables. So we can see rank contribution from each variable. Okay, and obviously, once we look at this tolerance value and we see that the variation is going outside our specified limits, we want to reduce the variation. So this is the first, you can say, the primary contributor which we should target, and we should ideally see if it is possible for us to reduce this tolerance value, maybe make it more precise to a lower value, let's say 0.1 instead of 0.3, and then we can instantly see what is the impact of it on the results. So results are calculated and updated instantly so that we can run multiple iterations. Okay. And because it is linked with CAD data, the assembly that we are using as input is the CAD assembly itself, your Trio or CATIA or NX assembly. So if at a later point, let's say you start a new design, you perform the tolerance analysis, get the results, but there are some changes required, maybe due to some quality issues in the product, maybe due to some thermal impact on the product, you require some changes in the design. So you can go back and make that change, and when you regenerate the model in CETOL, it will update those changes there also. So for example, if I'm changing this whole position, I'm moving this hole to this point. So it will update in the CAD data, obviously, when I make that change in CAD, but then it will also be updated in the CETOL data. So that's the benefit of having that synchronicity with the CAD data, and the changes are automatically updated. Now, mechanisms can also be simulated. So if you have products with moving components, like here in this case, we have this assembly with two assembly states, two assembly configurations, open and closed. So you might want to check the assembly variations with respect to open state, you may have different measurements required in open state as well as in closed state. So we can run through multiple, like we can define multiple assembly states, and then we can check what will be the part positions in open state and what would be the critical measurements with respect to that assembly state. Okay, so on the right side, you can see this image showing some animation. Okay, so what this animation is basically showing is that if the hole position, so the base part has a hole and the upper part, the cover, has a pin located in that hole. So if I'm moving this hole in vertical direction, translating it in vertical direction, that how that variation is impacting the measurements. So these green dimension arrows are showing different measurements, and the white arrow showing the position of that hole. So as the hole position changes, how the measurements are getting impacted. So that we can see in terms of this animation and also in the graphical view on the right side. Okay, and then we also get the sensitivity list showing that this left pivot hole has a sensitivity of 1.15. Likewise, all the critical features will show high sensitivity. So probably top 4 or 5 of these sensitivities are more critical. And you can say that the remaining ones which are having very small sensitivity like 0.15, for example, for this right pivot hole or for this datum B, we have a sensitivity of 0.12. So these are not as critical. So that way we can understand from the design perspective which features require better precision, better control, and which ones are there which don't require that much precision. So that's how we can reassign the tolerances, or we can redefine the GD&T based on that. Now within Creo, we also get these options for applying GD&T through that GD&T advisor option. So you can see in this model, we are just selecting the surfaces and then applying tolerances in the 3D environment itself. Now there are two major benefits of this. First is that this same GD&T, like obviously the first benefit is that the GD&T is more precise, more accurate. The tool is basically giving me a guided workflow for correct application of GD&T. So even if I'm not an expert in GD&T, I will still end up applying it correctly. Okay. Now the second benefit is that this GD&T once applied can be used for your 2D drawing creation. If you still want to create 2D drawings, you can just generate the 2D drawing with all the annotations, GD&T annotations in 2D. Now you can also export this as a 3D file itself. You want to share it with the supplier or manufacturing team as a 3D part with all the GD&T place. And the same GD&T is utilized for the tolerance analysis as an input when you're using it with CETOL. Okay, so there are multiple benefits for having a 3D based GD&T, and GD&T advisor basically helps you through that process. Okay, and once you have defined the part level tolerances, you get the results in terms of assembly variations. Then you can look at this contribution list, and then by changing these tolerance values, you can see the impact on the results immediately. So what you see in this graph is the worst case in statistical variation. So as I'm changing the tolerances for the critical contributors, top contributors, I can see the impact of it, how the yield percentage is increasing from 93 to now 99. So that's how I can verify, or you can say validate my design and tolerances and ensure that I'm able to achieve the then validation stage. Now, if you have some parts already manufactured, you have the sample data with you. Because obviously what we use in the tool is the ideal distribution, where we are not considering any manufacturing defects. But if, let's say, due to manufacturing defects, there is some variation, like the distribution is skewed like this. So what we can do is we can put the modified value of these just this is the moments of this distribution, like mean, standard deviation, skewness, and kurtosis. So basically, mean obviously is the mean of the distribution. Standard deviation gives you the amount of variation, and then skewness is a you can say measure of the asymmetricity of the distribution. If it is skewed towards the right or left. Okay, so that skewness, and then finally the kurtosis. So all these four moments are captured and put into CETOL so that we can actually check what will be the impact of using these parts in our assembly. So if the parts seem to be out of specification, we can still verify whether it will be fruitful to use those parts in the assembly or not. And if it is still okay to be used, then why should we scrap those parts? We can still make use of them and try to save some cost or scrap for the company. Okay, so now coming to the CETOL workflow. First, what we do is we start with the functional assembly interface. Basically, we tell the tool how the parts are assembled, how the variation is happening from one part to the other, what is the degree of constraints. Then we define the part feature control. Basically, we add up all the tolerances, like whether it is GD&T based or linear tolerances. We can do that in CETOL directly, or we can import it as a 3D annotation from CAD if it is defined in the 3D environment in the CAD data itself. So those are also imported automatically, and then we can, as I said, we can change the distribution if required. Okay, and then once we define the measurements, we can solve and get the results. And then look at results in terms of contributors and sensitivities. So this is the example which I will be explaining in detail. So this is automotive engine assembly, and just to show the parts that I'm considering here. So we have this engine block, oil pan at the bottom. The green part is oil pan, engine block, and then this crankshaft is placed in the center with connecting rod and piston. And on the right side, we have this water pump, oil pump. Okay, now first measurement is that I want to check is the minimum gap between oil pan and strainer. So here we have this pan, the green part, and the strainer, this yellow part. And what is the minimum gap between these two parts? Obviously, in the nominal condition, I can see that there is some gap, but I want to make sure that if the parts are manufactured at their worst case dimensions, at their extreme dimensions, what will be the impact of that on the assembly? Whether we'll still have some gap over here or not. Okay, so ideally we should still have some gap in every assembly that we're making. Right. That is the first measurement, avoiding interference or contact, you can say, in between these two parts. Now the second one is when this crankshaft is rotated by 90 degrees. Okay. I want to also check what is the gap between crankshaft and engine block over here. Right. And third measurement is when we are rotating it by 180 degree, basically at the lowest point for the piston. What is the gap between the piston and the engine block on this side, on the right side? Okay, so I'm just using these three measurements for reference, and then we are going through the assembly in detail, and then finding out what is the variation of these features. So on the left side, I have my Creo assembly, Creo window showing the assembly. So this is the okay, so on the left side we have this Creo assembly. So this is the assembly, oil pan. Then we have engine block, crankshaft assembly, oil pump assembly on the right side. water pump. Then we have some other parts like bearings for the crankshaft. Okay, so this is the assembly, and for reference, I'm just looking at the section view so that we can see all the internal parts. Okay, so on the right side we have CETOL. So at the top, what you see is this assembly name showing that this is the main assembly. Engine assembly is the main top level assembly. And then we have, just like we have the model tree in Creo, we have the model tree in CETOL showing all the parts that we are considering for the stack up. So it's possible that I don't want to consider all the parts for the stack up that I'm doing. So for example, in this case, this water pump is not included here because I don't actually require any measurements with respect to water pump for the analysis that I'm doing. I may require it for some other measurements, but for this case study, we are looking at 3 measurements, and that does not include this water pump. Okay, so basically these are all the parts which I'm including in my stack up. Okay, so the assembly shows this model tree shows all the parts that I'm considering in CETOL. And if I look at this engine block, for example, these are the assembly constraints which I have imported from Creo. So basically, while placing the engine block on top of this oil pan, we have a planar contact between the two parts. Then we have 2 locating pins. So basically, we are assembling this using these 2 pins. So there is one pin here, not visible due to the section view. So there's one pin over here and one on this side. Okay. Now for the crankshaft, we have show the crankshaft assembly. Yeah, so this is the crankshaft and another connecting rods. So these are the joints showing constraints between connecting dot. So this connecting dot is obviously defined as a coaxial, or you can say concentric joint with the crankshaft pin. Okay, so this is the joint between crankshaft pin and the connecting dot. And likewise for this piston also, we have some joints here. So the piston is placed within this crankshaft rod is placed within this piston. So and then we have the bearings in those parts. Okay, so likewise, if I go to the next part, we have this oil pump. So this oil pump is also constrained with the engine block. So there is this first contact, which is a planar contact between this surface from the engine block. Okay. And then we have fitting pins here also, one on the left side and the other on the right side. So basically, these are locating the oil pump, constraining it fully with respect to the engine block. First assembly state that I have defined here is when this crankshaft is at the current position. So basically, what you see right now is the 0 degree, basically the current position of the crankshaft, and I want to check this gap. Okay. So the gap between the oil pan and this oil strainer. Okay, so basically this is the measurement that is with respect to oil pan inside surface, and the other one is this strainer side surface. Okay. Now, if I wanted to do this manually, obviously I would have to define this stack up loop going from the oil pan to the engine block, then from engine block to the oil pump, and oil pump to oil strainer. So that would require multiple parts, multiple dimensions. That will take a lot of time defining those inputs, and it has to be done correctly. If I miss out on anything, it will give us, it will give me incorrect results. So here, what we are doing is we are simply defining this as a measurement. Okay. Now, for example, I want to create a measurement, let's say on this side, the distance between these two surfaces. Okay. So what I will do is I'll go to measure. I'll select the two references. This is from the oil pump, and this one is from the oil pan. So I'm defining this measurement, and I can also give it a direction, for example, perpendicular to this surface. So this is the measurement. And once I define this, right click and solve it, and then look at the results. So now this is showing me that this particular distance between these two parts, obviously it is zero, it is supposed to be zero gap, but if I look at the 3 sigma limits, it can go from minus 0.8 to plus 0.73. So this is the variation, you can say close to your 99.7, basically 3 sigma limits. And the worst case can go from minus 2 to plus 2. Okay, so this is showing the total variation that is possible between these two parts. And here we have all the contributors impacting this measurement. So here, in this case, the top contributor is the location of this surface. Okay, from the, so let's show the oil pan first. So this is the oil pan. So we are looking at only one part here. Here we are using this top surface as a datum. This is datum B, datum C. And then for the feature that I have defined just now, this side surface, here I have a linear tolerance for this surface, nominal value of 112.2 from the center axis, so basically from datum B. I have defined a linear tolerance of 0.5. Okay, and because it's a larger tolerance value, it is impacting more. So if I show you the results again, here we can see that the impact is 42%, roughly 42% from this variable. And then there are some contribution from other variables as well. Like this one is from the engine block. And this one is from the oil pump. Okay. So likewise, for this other measurement, the gap between the oil pump and strainer. This is the result. So I wanted to have a positive gap over here. Okay, so my requirement is not to have a symmetric, tolerance. My objective is just to have a lower limit of 0. So anything that is above 0 is fine with me. Okay, so I just want to have a positive clearance. That's it. So I put a limit of 0, and it is showing currently 91% yield, meaning that although the worst case is going from minus 2.1 to plus 2.7, with the nominal gap being 0.3. Okay. But 91% yield basically means that for 9%, you can say 9% of the assemblies will still have some contact here. And obviously, if there is some contact, it will impact the position of this strainer also. Either the assembly will not work or it will not fit. or it will, change the angle of this part. So basically we just want to have some positive gap here, and these are the contributors impacting this measurement. So if I look at this feature, this measurement, I may assume that the position of this surface is important for me, right? This surface, this is contributing 10%. So I may have assumed that this is the biggest contributor, but actually the biggest contributor is not this feature, it is this feature, which is the engine block side surface where the oil pump is located. So obviously the oil pump is having a planar contact with the side surface in the engine block, and because of the angular variation of the engine block, if the side surface is tilted, the oil pump will also tilt. So if I wanted to visualize this, maybe by just saying it will not be clear. So let me just show this animation. So as I'm rotating that side surface, the oil pump orientation will change, right? So this basically this oil pump will tilt like this, and that will have a impact on the position of this part. So obviously the oil pan, the green part is fixed in its location, but the yellow part, the strainer, which is assembled on the oil pump, which is again in contact with the engine block. So that's how the tolerances are driving from engine block all the way to the oil strainer. So if I wanted to reduce this, maybe let's say I just go to this, see what is the tolerance here. It is showing a tolerance which I can improve upon. Maybe I can bring it down to 0.2, for example. So I can see what is the impact of that on the results. So now it has moved up to 94%. Get the tolerances and then see what is the impact of each. And then I can also look at this sensitivities, linear or angular. So as you can see, this is highly sensitive. It is showing 2.7 mm per degree. So if I change this surface angle by 1 degree, this measurement changes by 2.7 mm. So that's very highly sensitive. So that's the reason this particular tolerance value becomes more critical. Likewise, for this second measurement, where we have this at 90 degrees, rotated at 90 degrees. So what I'm basically doing is I'm just going to rotate this crankshaft by 90 degree, and it will be like this. So what I'm doing is I'm just rotating this crankshaft. You can say anti-clockwise if you look at it from this direction. And then we are checking the gap between the crankshaft and the engine block over here, which is giving me a value of 2.5 mm nominal. Okay, but if I look at the results for this, I can see that it can go from 1.0 to 3.9. And then again, I can see all the contributors, like these are the top contributors. And the major contributor here is not any specific dimension, it's actually the float for this crankshaft. So like this is the bearing size mentioned here, 51.001 to 50.999, and this is the crankshaft size. So based on whatever clearance is there, there will be some float. So obviously if I look at this 51 for the bearing and then 49.9, so based on the amount of float, this part can move, and likewise it will be showing that total as well, like impact as a contributor. Then this one is the For example, this one which I'm looking at right now, it is for the crankshaft. So for the crankshaft, we have this feature having parallelism with respect to the center axis, right? So parallelism with respect to common datum AB or co-datum. So this variable, the position of the surface is also going to impact this measure. So likewise, I can see the impact of each tolerance value individually. Now get this third one. So here we have the gap between the piston and the engine block on this other side. And here what I'm doing is I'm rotating this crankshaft by 180 degrees, which will be having this position. So this is the gap which I'm checking here, which is 1.49. So basically, I can move the part positions with respect to any particular assembly state and define the measurements and then check the variation for those measurements. So if I look at this measurement now, this is showing me that the gap between these parts can go from 0.6 to 2.3. Minimum gap between these parts would be very close to zero. It is 0.6 and then these are the variables impacting this measure. Like this is Tx showing the this position of this this feature, this surface, position of this in the x direction. Tx translation in the x direction with respect to datum G. So what is datum G here? Datum G is this piston hole. And with respect to this piston hole, we have a position tolerance for this smaller hole. And Tx within this hole has a major contribution. So again, if I wanted to reduce this variation, let's say some limits say 0.2, for example. Now I wanted to reduce this variation, so obviously this would be the primary objective for me to try and see if I can reduce this tolerance. So if let's say I'm able to reduce it to 0.3, so I can see that now the variation which was showing earlier 0.6 is now 0.7. Okay, and the yield has also updated. So 0.5 it was showing 93% yield, meaning 93% of the assemblies are going to have variation within 1.3 and 1.7, but with a tolerance of 0.3, it goes up to 98%. Likewise, we have some angular variables also. So for example, this one is showing angular sensitivity. So this is basically showing the this crankshaft is assembled. So just show this feature first. This is the crank pin rotation along x direction. So if this crank pin is rotated in x direction, okay, in this direction basically. So if it is rotated by some degree in this direction, how that is going to impact the measurement. So obviously the connecting rod will be tilted, right? And that's how the piston position will also change. Okay, and then obviously I can look at all the other sensitivities as well, linear or angular. So like in this case, I can see that there are 6, angular sensitivities. Like this is for the connecting rod piston hole. Basically for this hole, piston hole in the connecting rod. So if I look at only the connecting rod, this is the piston hole. Which includes position tolerance of 0.1, which also includes the angular variation in y direction. Right? And obviously, if this angle is tilted, the piston will also be tilted. Okay, so these are the contributors and sensitivities. Now let me show you the part features also. Let me show the animation for this. So here we have the position of this surface as a variable. So when I run this animation, I can see the movement of the part. Obviously, it is scaled up by a factor of 5 because actual movement is not that much for this angular variation. So I am scaling it up to 5, but then I can animate and then understand how this part position will change, and accordingly what will be the impact of that on the critical measurement. So this will be a quick, give me a quick understanding how the assembly is behaving, and as a user I can understand it first, and then I can easily explain it to somebody else also. Let's say if I am talking to somebody from the manufacturing team, and we have, I have to give some justification for the tolerances that I'm defining there with the design. So I can have a discussion with the manufacturing team or with the supplier, and through these animations I can help them understand also. Rather than just putting it in a report and then sending it to them, I can just show these animations. So guys, please mention your questions in the Q&A section or in the chat box.
Perfect, Avichal. You took me back to engineering days. All my mechanical engineering days was back. Perfect presentation. Guys, please, if you have any questions, you can directly ask. I'll unmute you guys and then you can ask. If you do not have any other questions, we can.
Or you can mention your queries in the Q&A section or in the chat box, and we can take it up.
No, if there's no other questions, we'll share our contact information. If you have any technical questions, you can email or contact Avichal Sharma sir. Otherwise, if you want to buy the product, you can talk to me.
Yeah, so this is my information. If you have any queries after this session, you can contact me. Actually, the number is changed now. Just put the right number.
Perfect, Avichal. I don't think anybody has any other questions. Thanks a lot for attending, guys. So, do visit us. We'll keep doing a regular webinar every week. Okay.
And in the when you close the session, you'll see a feedback form, so you can also give your suggestions as to what other webinars we can do in future. So we'll take those inputs and probably try to include those things in our coming webinars.
Perfect. Thank
Okay.
you, guys. Thank you.
Thank you, Madan. Thank you guys for joining the session.